Now that you're familiar with the data organization, it's time to process the signal a bit so that it's easier to work with and easier to interpret. So this time course here shows the raw bold signal over time from one voxel that I picked at random. Well, okay, I didn't actually pick this number at random. I like how the number looks. But anyway, so we're going to apply two different processing steps to the time courses at each individual voxel. First, we want to transform the data into percent change, and second, we're going to detrend the data. So percent change is useful because it's a more easily interpretable metric compared to these arbitrary units here. And secondly, because percent change gets rid of this overall offset in signal intensity value. And these offsets vary over space, which happens in MRI data. Furthermore, you can see in the raw signal that there's this slight drift over time. You see that the signal is gradually going up over time. And so detrending the signal is going to get rid of this slow drift. Now, after applying these two steps, we can recreate this plot, and you see, the y-axis values have changed because this is now percent change. And you also see that this slow upwards going drift is removed from the data. After completing these two steps, we're also going to go back to the two plots from the previous video that you can see here. We're going to recreate those two plots using our newly processed data. Now, the color scales are not the same between these two figures, but you can see that they are similar but not identical. All right, so now let's switch to MATLAB and get coding. Of course, you should feel free to pause the video and work through the code on your own before watching me explain it. So we start by generating that plot that shows the time course of activity from one voxel. So here's the voxel that I picked, and you can see how I'm setting up this subplot. So I have a subplot of 4 rows and 1 column, and then we are going to plot into the middle 2 columns. So you'll see what this, actually I'll already generate this subplot. Okay, so here you see, it's just a axis that doesn't span the entire figure. And let's see, I also need to define this voxel to plot. So what we want to do here is create a time vector in seconds. Now we can create a time vector that's something like this, that would go from 0 to the number of time points, which is the size of data, comma 2, and then that has to be -1 because I'm starting at 0. Now this is okay, except this is not going to give us time in seconds. This is just time in TRs, or repetitions, or indices. So to convert this into seconds, we need to divide by the sampling rate. So what is the sampling rate of these data? Well, let's look at TR. So we have in this data set that we've imported a variable called TR, and we can see that that happens to be 1. So this is in seconds. This tells us that the repetition time is seconds. And so to convert from the repetition time in seconds into a sampling rate, we actually need to divide this by 1. Now, in this particular case, it seems a little silly to say 1 divided by TR, because 1 divided by 1 is still 1. But there would be other cases where the repetition time is 2. 2 seconds is a pretty common repetition time in fMRI, in which case the sampling rate is 0.5 hertz. So we need to divide this time vector in indices by the sampling rate, which is 1 divided by TR. And this is going to give us our time vector in seconds. Okay, so then we want to plot the data from the selected voxel over time. So we have time, and then we want to plot data. And again, I'm using the data from the first run. That's just for convenience. You can try plotting it from some of the other runs. Okay, and then we want, let's see, so this is going to be all of the time points, which is the second dimension, and only one of the voxels from the first dimension. So this is voxel 2 plot, comma, all. Okay, so let's run this, make sure that looks good, and it does. And then I'm just adding a few lines just to make the plot look a little bit nicer. So I set the x-axis limits to go from the beginning to the end of time, and that just makes sure that we get rid of this white space over here, and add a couple of labels. And this looks Okay, I was going to say it looks pretty good, except that we get an error here. And in fact, we have another comment here that says, so clearly something is not right over here. Well, what do we want to do? Well, it looks like we want to concatenate this string, this text, with this number so we see which voxel we're plotting. So first of all, we know that we can't directly use a number as a string, so we need to convert this. I'll write num to string. And then this still isn't actually going to work. And the reason why this won't work is because we need to concatenate these two strings. And the way that we concatenate strings in MATLAB is with square brackets like this. So we put a square bracket before the beginning and at the end. And that is going to give us our correct title with no error messages down here. All right, very nice. So now we've created this plot. And now we want to convert to percent change and then detrend. So let's have a look at this for loop before we worry about all of the details. So it looks like we're looping in so we're going in a loop over the different runs. Now this is supposed to go from 1 to 4. If we go, if we just set the looping index to be 0, then it doesn't matter what code we put in here, that won't get run. So that's clearly incorrect. So this needs to go from 1 to the number of runs we have, which is the length of data. Remember, data is a cell array with 4 elements in it. So the length of data is 4. So we're going to loop over each run. Here we are converting to percent change. And well, the formula for converting something into percent change is the data minus, so in general, it's A minus B divided by B. And since we're computing the percent change relative to the mean, because that's our baseline in this case, then it's the data from this run minus the mean, and then this should be divided by the mean. So that we don't want to multiply. We divide by the mean, and then so this formula right here gives us proportion, and then to convert to percent, we have to multiply the whole thing by a factor of 100, not a factor of pi. I hope you enjoy working through this code. I also, it's quite fun working through this. Okay, so then here we are computing the mean of the data points, and we want to compute the mean over time. So this has to be the dimension, has to be 2, because we are computing the average over time. Now you can see this is also a variable that I've created here just for convenience. You could have done this whole thing in one line of code by writing it all out like this, and then you don't need this line anymore. Now there's nothing wrong with this line of code, but I think it's a little bit long, it's a little bit tedious to look at, and that means that you're more open to making mistakes. There's more possibility for making honest coding mistakes with a long line of code like this, particularly when you're repeating things. So therefore, my suggestion, my recommendation, is to separate this into 2 lines of code. Okay, very nice. And let's see, then we need to detrend. So here I say, note the orientation. So let's actually have a look at the help file from the detrend function. Now you know from earlier in the course that you can type help detrend, but I actually find it more convenient just to open up the file and read the help message right at the top. Then I don't have to worry about scrolling so much. So let's see. So detrend removes the best fit line from the data, and we want to know what happens if X is a matrix, because that's what we're inputting into the detrend function, a matrix. It removes the trend from each column of the matrix. Let's go back. So data are always organized as rows by column. In fact, we want to detrend this data matrix row-wise, which means that we actually transpose it so that so the rows become columns and the columns become rows. Now, when we run the detrend like this, that's actually going to flip the orientation of the matrix. So therefore, we have to transpose the output again. So it's a little weird to have a double transpose like this, but that happens in MATLAB encoding, that you need to be mindful of these orientations. Okay, so let's run all of this code here. And very nice. Now that that is finished, we can rerun figures 1 and 2 in new figures. So we want to recreate this figure and this figure with our new data. Notice I've overwritten the data variable, so we no longer have access to the original data. Okay, so let's see. So that means that when we go back here, we need to change this figure number, because if I left this as figure 1, it would completely overwrite this figure and we'd lose this information. So I'm going to change this to figure 3, and then we don't need to run all this because we've already run it. So we just need to run the plotting code. So that's this and this. And then I can also set axis image just to make it a little bit more comparable. Although I think here I had axis square, so I'll also rerun axis image there. Now, these are not yet visually comparable because they have different color maps. Remember, I changed this one to jet, so therefore I'm also going to change the color map here to jet to make these more directly comparable. And I see now that these two figures are identical because I just mistakenly said we don't need to recreate these variables. Of course we need to recreate the variables because we changed the data. Okay, so I reran that code and rerun the standard deviation map. And then we can redraw this. Okay, so redraw figure 3 from scratch and the other plot. Now here you can see the standard deviation is much smaller. So this standard deviation map from the original data and this standard deviation map, they are hardly comparable when leaving them with the same color limit. And that's because of the signal inhomogeneities across space, leading to much higher standard deviations, which we got rid of by removing the linear trend from each individual pixel, from the time course from each pixel. So let's see, I forget exactly how I set this in the slides. I think it was maybe a little bit smaller than this. And finally, I want to recreate figure 2 so we can compare the bold time course from this same voxel before and after the two signal processing methods. So that was, let's see, that's here. And then of course we want to change this to figure 4. And let's see, I'll run all of this code just like this. And now it's really clear when we go back and forth that there is a trend line that's been removed.